Okay, recording, and let me get chat going. All right, here's a big chat thing. I guess this pointer's big enough for you to see. Let me make this a little bit bigger so that if some of you are looking at this on an iPhone or some other. Damn, this thing keeps coming at me. It's just so damned aggressive. All right, well, that's maybe a little excessive. Let's see. Okay, so let's just remember that the singular value decomposition is, in fact, let me switch over here to the iPad. The idea basically is that you choose a basis in the domain space and a basis in the range space, and then the operator, and you choose the right basis, the basis such that the L's are the eigenvectors of the operator A, and the K's are the images of the, the BJ's are the images of the AJ's under the action of, that is to say, BJ is AJ, and of course, AJ is an eigenvector, and I don't remember quite what I called it. Let me just call it alpha J at the moment, because there's a square root that's involved here, and so consequently, in terms of these, the BJ A element is so AJ of course is equal to alpha J. Well, let me get back to the original description here. So it's US V adjoint. So any rectangular complex matrix can be written this way. And as I said, the basic trick is to choose the right bases in both spaces, and then you get to express the operator A in this way. And let me just get that's right. The eigenvectors of A, of course, aren't necessarily positive at all. It's that the square of the eigenvectors A is equal to the singular value. So the singular value, this on that would be the eigenvector, the eigenvalue. This is the absolute value square of the eigenvalue. So I guess I never wrote down the eigenvalue itself. So let me just write a note to myself. I probably should have done that. Anyway, what one gets is, of course, this expression for A as in terms of the two chosen bases or bases, or equivalently as in matrix form, A Kj is this sum here. And let me make that clearer. What I wanted to mention to you once again is that I've gone too far in each case. That if you write A in terms of these two in terms of any two bases, then you get it in this form here, and then the KBIs are the matrix elements of the unitary operator U, and the AJLs are the matrix elements of V dagger, and so that's what I was trying to illustrate here, which I was writing up before mentioning these things to you. I think I'm actually going to go a little bit off what I originally intended as the script. Namely, suppose A is equal to A dagger. Then we might have A on AJ. Well, let me call that alpha J, since I didn't have a formula for it before. But then, actually what we said was that these are the eigenvectors. That's right. We started out with the eigenvectors of, I want to get the eraser again. So this is what we called SJ. Those are the A's are the eigenvectors of not of A. I mentioned I misspoke a few moments ago. The A's, the special basis in the domain space. These are the eigenvectors of A dagger A, which is automatically Hermitian. Now, if this is true, then that becomes A squared AJ equals SJ AJ. And so then the SJs are effectively the squares of the eigen values of the operator A. So in other words, A is Hermitian now, and so A does have alpha J, AJ as eigenvectors, and SJ is equal to alpha J squared. That's in the case when it's Hermitian. And then the singular value decomposition of A is just U S U dagger, because you can have the same or V S V dagger, because Hermitian operators can be diagonalized by unitary transformations. And this S is it's not quite, you see, normally when we diagonalize a Hermitian operator, we just write the eigenvalues on the diagonal. Here, what we do is we change the phases a little bit of these eigenvectors of A. So that, in fact, what we have here is just a positive matrix sigma. And now in the case, on the other hand, where A is a normal, not a normal matrix, a unitary matrix, then A dagger A, of course, is simply the identity operator. And so as the special basis you're just dealing with the eigenvectors of the unitary operator, but every vector is an eigenvector of the unitary operator. So the basis in the domain space is arbitrary. You could use it as just the vectors k. Any set of vectors k would be a suitable basis in the domain space, and then A would map these bases into new vectors, which we would call, I guess, BK, and so one would write this. Now we would be writing this unitary matrix then as a sum on BK. So BK, A, KK. So the basis here is arbitrary, and whatever it is, the B's are whatever A maps the K's into. And so this would be the representation then of A for the unitary case. So I just thought I'd sketch that out a little bit for you, just to remind you, just to reinforce your understanding of Hermitian of the singular value decomposition, because as I said, that's the most important thing, really, or one of the most important things in linear algebra. If you guys have a question, and you can just type it into the chat session, and I can see if I can answer it for you. So I just find these two examples of the singular value decomposition to be amusing, and that's why I thought I'd mention them to you. Well, I'm going to now skip to the second chapter here, and as we start, I don't know what is going on with, oh, it's see, I'm using a colored large pointer, and that means that everything is just a little screwed up. When I point to something, this computer doesn't quite know how to interpret the big mouse. Well, you guys know what a derivative is, so I'm not going to go through this. And I assume you know what a partial derivative is. It's a whole derivative of a function with the other variables held fixed or constant. There is some notation, though, that I thought I'd mention, and it's something that I lapse into just without even thinking. F prime, for example, is a derivative. F double prime is a derivative. F dot is notation for time derivative. That was Newton's notation, actually. F double dot is the second time derivative. Sometimes one uses F parenthesis K parenthesis for the kth derivative. And if you have two variables, function of two variables, FKL is a double partial derivative. Other notation, which is convenient when you have 2 or 3 variables that you're labeling as X, Y, Z, something like that, then F sub X or F comma X can be the derivative partial of F with respect to X. F sub X, Y, Y, or F sub comma X, Y, Y is the third derivative, first once with respect to X and twice with respect to Y. And these, since X and Y are independent variables, you can commute these derivatives, so you can have you have the partial F, partial X, partial Y is the same thing as partial f, partial y, partial x. What's a little tricky is that you can think of a function as a function of two real variables. Sometimes it's written as a function of two complex variables, and I see there that I need to put in an upper index there. Oh, Christ. I screwed up. I introduced an error in the text file. I'm now trying to fix it for you. I have, oh God. All right, I'm truly sorry about this. The error seems to be on line 10873. So that all right, let me. My goodness, 10873. That's an awfully long way. Sorry for this. Okay, what did I do? 8. Boy, I do not understand at all what has just happened. I tell you what, just because these tech issues take an arbitrary amount of time to figure out, I am going to use instead the whole book thing, and I'll make this bigger. Let me shrink this. Let me make this bigger for you. Okay, so complex differentiation. Actually, I want to fix this here, but in order to do that, so Z and Z star, and where Z is X plus IY, of course, Z star is X minus IY. So the partial derivative with respect to X and Y can be related to those with respect to Z and Z star in this way. And let's see, I'm going to switch to blue now. In other words, suppose F is equal to Z squared Z star. Okay, so then partial F partial Z would be 2Z Z star. Partial F partial Z star would be Z squared simply. And then the reason why partial F partial X, which I've written here as F sub X, what would that be? Well, it would be partial F partial Z times partial Z partial X plus partial F partial Z star partial Z star. partial x. And partial z partial x is just 1, so this is partial f partial z. Partial z star partial x is also 1, so this is plus partial f partial z star. So that's this equation here. If you do the same thing with respect to y, partial f partial y is partial f partial z partial y. Well, that's going to be I, and then you're going to have partial f partial z partial z star partial z star partial y, and so that gives you I partial f partial z minus I partial f partial partial z star. And so that's this equation here, and then you add and subtract and you get these equations. So the thing that's confusing and somewhat disturbing here is that in order to carry all this out, which is sort of a notational convenience, you have to regard z and z star as independent variables in order to differentiate them the way I was. And they're of course not independent. Z is the complex conjugate of z star. And so you're just to, when you do these derivatives, you're just to imagine this as a formally a function. You just regard z and z star as independent variables, and it's anyway, it's notation. I hope that looking at this will clarify it for you. We occasionally will use it just as a convenient notation. Gradient. Well, so what I'm going to do now is I'm going to go through these various things in vector calculus, which you probably all have learned in one way or another as undergraduates, or in graduate school. I don't know. Anyway, gradient, curl, divergence, Laplacian, and I think it's good to hear about them formally from a somewhat mathematical point of view. So the change dp in a point P due to changes in its orthogonal coordinates. And in fact, in a sense, this is a definition of the term orthogonal coordinates. The idea is that the coordinates are orthogonal because when you change the coordinates, the point moves in 3 different directions, E1, E2, E3, and these directions are mutually perpendicular. These E's can have their own lengths. EI is of length HI, but they're certainly orthogonal. And so in these orthogonal coordinates, then dp is given by the partials summed with the differentials, and so it's EI dui, and so EI dui summed from 1 to 3. And if one makes the vectors orthonormal, then in terms of the orthonormal vectors, we put in these lengths h. And in 3 dimensions, the orthonormal vectors have cyclic cross products. This is a property of 3-dimensional space, and namely that you can define this cross product of 2 vectors and you get another 3-dimensional vector. Epsilon, of course, is this antisymmetric symbol with epsilon 1, 2, 3 equal to 1, totally antisymmetric. And so in other words, that in rectangular coordinates, you have this, in cylindrical coordinates, you have that, and in spherical coordinates, you have this. And the point can be written in terms of the cylindrical and spherical coordinates, but using the basis vectors x, y, z like this. And then you can find what the hat always means, or almost always means, unit length. And so the unit length vectors rho hat, phi hat, z hat look like this. R hat, theta hat, phi hat look like that. And now the gradient of a scalar function f is defined so that its dot product with the change in the point P is the change in the function. So in other words, we now know what dP is. dP is this thing. And so dF is said to be the thing that dotted into dP gives us the change in the function dF. And so the E hat i's are orthonormal, and so what we get is this sum, the first component of the gradient times h1 du1, and then so forth for 2 and 3 is df. And so then, but then that's also just by ordinary calculus, partial f partial u1 du1 and so forth. So comparing the coefficients of du1, you see that this gradient is E1 hat over H1 times the partial with respect to U1 plus the same thing for indices 2 and 3. In rectangular and spherical coordinates, looks like this: rectangular, cylindrical, spherical. And one special case of the gradient is that we'll come back to is the gradient of 1 over r, and it's minus r hat over r squared. That's something that you undoubtedly have done many times in when taking electrodynamics, and electrostatics is very much the consequences of these equations. And here, this gradient is with respect to r. The integral of the gradient of a function over a volume is equal to the integral of f over the surface. So in other words, we see that in one dimension by saying the integral of from a to b of f prime of x is of course f of b minus f of a. The analog in 2, 3, and n dimensions is that the integral of the gradient over a volume is the integral of the function over the surface. The next concept is the divergence of a vector. And the definition that I'm using here is that the divergence of a vector in a tiny cube is its integral over the surface divided by its volume. And the surface integral, on the other hand, is V1 integrated over the one forward face minus integral of V1 over the backward face, in the face that faces in the -1 direction. Anyway, you've got to do that over all 3 cases. And so it's basically V1 integrated. You see the, all right, let me draw you a picture here. Okay. So suppose this is the one direction. So this might be H2, and this might be, whoops, H3. So the area of this is H2, H3, and you'd have this would be the V1 which is pointing out this way, V1, H2, H3. So that's the integral of V1 over this face. But then we have to also consider the integral of V1. Well, actually, V1 is still pointing. If V1 is pointing this way here, then oh, nuts, I'm going to have to erase some of this. Then here, V1 is also pointing like that. And then you have, again, H2 and H3 here. But H2, H3, and V1 are different on this face. Oh my God, I wasn't showing you this. Are different on this face from what they are on the back face. And so what you've got to do is you've got to take the derivative of this with respect to U1. And so that gives you the then surface integral the volume then is H1, H2, H3, du1, du2, du3. And so the ratio of the surface integral, which is du1, du2, du3 times, well, this is, for example, one face. This would be this times du2, du3. And so the divergence is the sum of things like this for each of the three directions. So you have, for example, this face minus this face, and then this face minus this face, and then the top face minus the bottom face. And that gives you these three terms. And you differentiate because you want the value of on the front minus the value on the back. And so this is the general formula in orthogonal coordinates. And in rectangular coordinates, it's very simple. The H's are all unity. And it's just partial of V x respect to x and so forth. In the cylindrical coordinates, it looks like this, and in spherical coordinates, more complicated. But it goes from all these two formulas follow from the previous formula, just using the values of H1, H2, and H3 that we found earlier. And now, if you take a bunch of these cubes and just add them to, what you do is you make up a given volume that looks sort of like this. You make it up by putting a lot of these cubes one next to the other until it looks somewhat like this. And what you can see happening here is that the outer going face here of this first cube, the surface integral of that is canceled exactly by the surface integral of the over the second cube, because in the one, it's the same vector and it's regarded as going out in one case and going in the other. And the same thing for example, this face, those integrals cancel. And so what happens is all the interior faces cancel, and all you have is the surface integral. So you just have V dotted over the surface, and this is the integral of the divergence over the whole volume, then is the integral of the function dotted into the surface. And that is one of Stokes's theorems. Stokes actually was quite remarkable. This was just one of several theorems, and he didn't just, his main work was not inventing the theorem. His main work was, he invented the theorem in order to use it to do something that was much harder. That's typically what happened in all these cases of these, when we cite famous physicists and mathematicians, and we cite them for a particular theorem or formula, and typically it's not what they were trying to do. Typically it's what they did in order to do what they were trying to do. And so in fact, we cite Newton as inventing the derivative, Newton and Leibniz, but Newton and Leibniz were trying to do much more complicated things than differentiate ordinary polynomials. They were using the calculus to do very complicated things. That's a kind of humbling thing when to learn. So I feel appropriately humbled, that maybe you would also. Normally I skip the examples, but in some cases it's useful. And so, for example, the integral of the divergence of the gradient of -1 over r over any sphere, however small, centered at the origin is this. So the divergence of this integrated is the integral of r hat over r squared over the area, and dA is r squared r hat d omega. The r hats give you unity, the r squareds cancel, you just have d omega 4 pi. So this is a quite remarkable formula. Namely, you take the divergence of r hat over r squared, you integrate it over an arbitrary, any arbitrarily small sphere that includes, or surface, I should say, over any volume that includes the origin, and you get 4 pi. If it doesn't include the origin, you don't get 4 pi, you get 0. And so if you, instead of using the origin, you just take the divergence of r minus r prime, or well, over r minus r prime, length of r minus r prime cubed. What you have is this integral over the surface, and that again is 4 pi. So this is quite remarkable. You take integrate the divergence of this thing over any volume, however small, that includes r prime, and you get 4 pi. And so what we say then here is that this thing is a delta function. It's a representation of the delta function. And why is that? Well, it's that if you integrate f of r times the divergence of this r minus r prime over r minus r prime cubed, you get 4 pi times the value of f at r prime, as long as you integrate over a volume that includes the point r prime. So that's an example of a delta function. You should read that example. The Laplacian now is the divergence of the gradient. So in orthogonal coordinates, it is grad squared on f. So, I mean, what it really is it's the divergence of the gradient. And then we rewrite that as grad squared, meaning grad dot grad. And on the other hand, that's a lot of writing, and so people often write this as triangle. And just combining these two formulas, the formula for the gradient and the formula for the divergence, this is what you get. In rectangular coordinates, it's simply that. In cylindrical coordinates, just putting in the different values of the h's, it's this. And in spherical coordinates, it has, in general, this form, but that turns into two interesting forms that differ according to how we write the R form. And it can be written as 1 over R squared d by dr of R squared times df dr, or it can be actually FDR. Those are the initials of one of our great presidents, Franklin Delano Roosevelt. Anyway, or you can also be written as 1 over R, second derivative with respect to R of RF. So those are two different correct ways of writing the Laplacian there. In these terms, one can rewrite the delta function example as minus Laplacian of 1 over R is 4 pi delta of R, and minus Laplacian of 1 over R minus R prime is 4 pi delta of R minus R prime. Sometimes people write just, hold on, people just write delta of R. Sometimes people write delta cubed of R. This is if R is a 3 vector. Sometimes people write delta 3 of R. And they all mean the same thing. And it's just, people want to be really, really clear. Well, also use, let me rewrite this in a way that is a little bit clearer. So people who want to be really clear, use this form. People who just want to be succinct use that form. This is an example that you should read at your leisure. Although I realize that leisure is a word that graduate students do not understand and do not have the use of. The directed area of an infinitesimal rectangle whose sides are the tiny perpendicular vectors hi ei hat dui and hj ej hat duj is their cross product. So it's just basically that if you have here one vector this way, another vector that way, then the cross product, so this is, let us say, AB, and then this is A cross B. And that cross product looks like this. And a nice way of writing the cross product, as we learned earlier, in fact, you, I hope, learned it in college, it's the sum on K, a totally anti-symmetric symbol, epsilon ijk, ek, hi, hj, dui, duk. By the way, people sometimes, and in fact, I probably sometimes write epsilon ijk as e sub ijk. I don't know. I think I try to write it as epsilon, and then of course LaTeX has two different epsilons, and I probably always use the simpler one, the one that's simpler to write in LaTeX. The line integral of a vector f along the perimeter of this infinitesimal rectangle. So the rectangle in this case looks like that. And we're going to integrate chug, chug, chug along, chug, 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 chug. And basically, this integral, to some extent, this integral typically cancels most of that one, and then this one cancels most of that one's, and in the sense that we subtract in doing this integral, you see you're going this way and then you're going that way, and so typically there's some cancellation there. Let me just see if I can. Good. Okay. And so what is that integral? Well, it's Hj Fj, and that would correspond, let us say, to this integral here, Hj Fj duj. But what we've got to do is subtract the green part, and so we differentiate this with respect to ui, and then multiply by dui, so as to subtract the green line integral from the red one. And so what we have then for this integral of f dot dl is dui duj of these two, the difference of these two partial derivatives. And so it's so what do I want to say here? So we're integrating f along this around this loop, and so the curl of the vector f is defined as the surface area, as a vector such that dotted into the surface area, you get the line integral around the loop. And so the kth component of the curl then is epsilon ijk partial of hj fj with respect to ui, and then dividing by the two scale factors. And so if we write the whole thing as a vector, then we sum over the orthonormal vectors ek. We have the antisymmetric symbol, the two scale factors, derivative, and then hj fj. And in rectangular coordinates, it's very simple. It's simpler. It's because all the h's are just one. All the h's are just one. The ith component is the epsilon ijk, the antisymmetric symbol, partial j of fk. And one can remember when we skipped over the sequence of determinants, you might have noticed that the determinant is basically it's a sum with the antisymmetric symbol, and that's the determinant of this kind of a vector. And we divide by h1, h2, h3 to cancel out the extra h's in here. But we need some of them because it's derivative of hj fj. So that's where we have the h's, h1, f1, h2, f2, h3, f3, the derivatives, and then the vectors in these various directions. And these h's are to cancel the extra h's here. In rectangular coordinates, as I said, it's just very simple. The x hat direction is the y derivative of fc and so forth. In cylindrical coordinates, whoops, it looks like this. And in spherical coordinates, it looks like that. And then one example is the magnetic field in the z direction. And one way to think about it, to represent it, is to say it's 1/2 B0 rho phi hat. And you take the curl of that in spherical coordinates, then what you get is B0z. Maybe I should sort of do that for you. This is a case where there's only one component. So the curl B should be 1/r² sine theta. I'm doing this live, by the way, so oh, this is going to be complicated because it's unfortunately this is going to give us the curl in the z direction. Let me actually grab something from something else that I was working on. Oh God, where did I put it? I don't remember where I put it now. All right, let's instead do this. Let's suppose A is equal to y x hat. So then curl of A, it's going to be this sum epsilon ijk partial j ak. Well, the only A is A1. A1 is equal to Y. All the others are 0. So this is epsilon ij1 partial j of Y. Right. And now the j, the only j that works is j equal to 2. So this is epsilon I 2 1 just times 1, and this then means that the curl of A, the ith component, I has to be 3, delta I 3, and we see we have a minus sign. So what I wrote here then, this means that B, so B points in the z direction, and B is then the vector minus, in fact, it's just the vector minus z hat. So it's a unit vector in the z direction. I lapsed into rectangular coordinates just because I didn't want to screw around with all these trigonometric functions. We can get another of Stokes's theorems if we take an assemblage of rectangles and make the surface, make a surface out of these rectangles like this. And what happens now is that these interior line integrals all cancel. And what one has then is simply, what survives is simply the line integral along the, the line integral along the perimeter. And so what this says is the integral of the curl of F over the surface, well, that's the same thing as the integral of the function F around the perimeter, the total boundary of the surface. And so what we were doing was we were adding up a bunch of little integrals. But here, you see they just cancel. And so what one gets is another one of Stokes's theorems. In empty space, Maxwell's equations are in empty space, divergence of E vanishes, divergence of B vanishes, curl of E is minus B dot, and C squared curl of B is E dot. And they imply the voltage induced in a loop, E dot dx, is minus the minus B dot integrated over the area. In other words, it's the curl of E over the area. So let me just say, I should have added del cross E into that equation. The magnetic induction induced in a loop, that is to say, induced in the area enclosed by the loop, is, well, B, we're dealing with the curl of B, and the curl of B is E dot, and so we have E dot integrated over the area. So if you have area, if you have the electric field changing in an area, then you get a B field. So then there's the Laplacian of a vector field, and the Laplacian of a vector field is more complicated, obviously. And here, what one does is use we use two Levi-Civita identities. This looks totally bizarre and hopeless, but in fact, if you learn and remember this, it will be your friend and help you out in difficult situations. So the sum on so if you have a product of two anti-symmetric three symbols, then they're equal to the product of the delta functions that sort of match minus the delta functions that don't match. If you sum over, if you have the product of three symbols in which two indices are repeated, then and you sum over them, you then get twice a Kronecker delta of the remaining indices. And what you find from that is that the curl of the curl is epsilon I j k g j epsilon k m n d m a n. This thing turns into a bunch of deltas, and that gives you the ith derivative of the divergence minus the Laplacian of the ith derivative. And so the general expression for the Laplacian of a vector field then is this. And in fact, in many books, that is the definition of the Laplacian of a vector field. It's the gradient of divergence minus the curl of the curl. And if one applies these to Maxwell's equations, then you get the curl of the curl is the gradient of divergence minus the Laplacian. In empty space, the divergence of E vanishes, and you just have Laplacian of E, but E is curl of B dot in empty space, and that then, and the curl of B is E dot, and so you get minus E double dot over C squared. Similarly, the curl of B gives you minus B double dot over C squared. And now if you combine this piece with that piece, you get this equation. And if you combine this piece with that piece, you get this equation. And these simply are the wave equations for the electric and the magnetic field in vacuum. And the solutions are very simple. It's just some vector times e to the I k dot r minus omega t, where omega is k, length of k times c. And let's see. I have here k hat dot epsilon. You don't really need k to be perpendicular epsilon for the electric field. Well, for a light wave you do, so a plane wave you do. All right. Anyway, let's go with k hat dot epsilon, or k dot epsilon equal to 0. The next topic here is the Helmholtz decomposition. And this is an application of the delta function formula we saw earlier, that minus Laplacian of 1 over r minus x is the delta function of, this is, in other words, minus Laplacian 1 over r minus x is equal to delta of x. And so I'm just doing it like that. Now, these derivatives are with respect to, I'm taking them with respect to r. And so one can write v of x as an integral v of r over times this delta function minus Laplacian 1 over r minus x, integrated over all space or integrated over a volume that includes the point x. And then since the derivatives with respect to r, you can pull them outside. Well, no. What you do is they can be with respect to r or with respect to x. And taking them to be x derivatives, what we get is we can pull a Laplacian outside. Oh, damn it. I just wanted to move that out a little bit to see the number. All right, let me just move this over so we have more space here. So now, we now take the curl of the curl, or Laplacian on V, I should say. What we get is that, in other words, this Laplacian is then minus the gradient of the divergence of this thing plus the curl of the curl of this thing. And so what have we said here? What we've said is we can write an arbitrary function as minus the gradient of something plus the curl of something. And the first something is a scalar, and the second something is a vector. And so we can write an arbitrary three-dimensional vector field as the gradient of a scalar field plus the curl of a vector field. And the scalar field is this first component here. And this is the derivative with respect to x here. We can bring it inside and make it a derivative with respect to r. And it seems to me when you bring it inside that there's a minus sign that occurs there. So let me just. So in other words, this derivative is just the x derivative. We bring it inside, it's an x derivative. We switch it to an r derivative, and there actually should be a plus sign here. So I am going to write this as a plus sign. And on the other hand, we can also say it's the curl of the vector, the quantity A is this quantity here, and this is the curl with respect to R of this, and so it's boy, I am really, oh no, this is the X, this is the curl with respect to X, of course, here. And when we bring it inside, we have curl with respect to X, and that gives us minus the curl with respect to R. So there's also a minus sign here. And so let me all right, so I'm going to have to make sure that these corrections need to be made, and then I'll add it to the errata for the book. Anyway, von Helmholtz was of course, a major physicist in the 19th century. Well, we've got almost 10 minutes left, so I guess there's no need to hurry through the rest of this. Magnetic field can be written in this way. You then have the gradient, the divergence of the magnetic field. Well, there is no divergence in the magnetic field, so it's automatically the curl of a vector field. Also for an incompressible fluid, what you have is that the divergence of the velocity flow vanishes. By the way, the term incompressible fluid is not meant literally, because any ordinary fluid is compressible at some pressure. But most fluids are incompressible except under very, very high pressure, and so they're loosely referred to as incompressible. Now here's Dirac's delta function again. As I said, it's a function, or mathematically it's a functional, which is to say, you know, a function is a map, numbers to other numbers. Or as we often say, x to f of x equal to y. A functional is a map from functions. And in fact, let me not use from functions to some number, and if it's a delta function, then it's to a number f of x, and this is the case for a delta function. And I'm sorry I didn't show you that. So function goes from x to f of x, which we might call y. And on the other hand, a functional is something that goes from a function to a number. And if it's a delta function, then like delta of x, then it goes from f to f of x. So this is for the case delta of x. And so in other words, the delta functional operating on the function f and associated with the point A is f of A. And in physics class, we write it as an integral of f of x times delta of x minus a dx. And mathematicians made this rigorous and generalized it and so forth. And what they did was they said, well, we can differentiate the delta function, and it's defined. The derivatives of the delta function are defined so as to make integration by parts automatic. So f of x delta prime of x minus b is minus f of x delta of x minus delta minus f prime delta of x minus b, which gives us minus f prime of b. And this delta double prime of x minus c gives us f double prime at c. And for several variables, they work the same. The delta function of a function and a point A is the integral of which is equal to integral we write as integral to f of x delta of x minus a. It's f of a. And we can imagine delta functions as looking like this in 1 and 3 dimensions. Now, a really important point in general, and especially in general relativity, is the notion of a covariant and a contravariant vector. And if we have a general coordinate transformation from x, which may be coordinates in 3-dimensional space or 4-dimensional space or 10-dimensional space, if you go from x to x prime, the derivatives transform this way. In other words, the derivative of x prime 9, say, is the sum from 0 to 10, say, of the partial of xk with respect to x prime 9, I think I said, times the partial with respect to x k. And a vector that transforms like a partial derivative symbol is called a covariant vector. So this is covariant vectors are vectors that simply under arbitrary coordinate transformations transform like derivatives. So it's really a very simple concept. It's just calculus a little bit multi-dimensional, vector calculus a little bit generalized and formalized. Coordinate differentials are even simpler, and dxi prime, well, just the chain rule tells us that this is the sum of partial x prime I with respect to xk times dxk. And a vector that transforms that way is called a contravariant vector. I don't quite know why one is co and the other contra. Covariant vectors have lowered indices. Contravariant vectors are often written with raised indices. So we've got a minute left. This is a good time for somebody to ask a question. By the way, I met with students on Saturday afternoon at 5 o'clock. One person showed up. I mentioned to one of my sons that only one student showed up, and he said, well, meeting on the weekend is a hard sell for a student because this weekend is their weekend. And so would you guys rather that I try to meet with you on Monday afternoon rather than Sunday afternoon? As I said, this past weekend I was in the courtyard of Pais on Monday at 5, on Saturday at 5 o'clock. This weekend I could do Saturday, Sunday, or Monday. And if there's a preference, I think I could follow that preference. So see, the problem with Monday is that some students have class Monday at 5 o'clock. So offhand, I'd say Sunday would be best, but I realize Sunday is your weekend, and so I don't know. All right, somebody says weekend is better. I think that's the person who actually showed up, which means he gets 2 votes. But there are 16 of you, so if you want Monday, let me know. All right, we're now kind of over time, and I still don't see a question. The homework assignment I've mailed to you, and it's also on the class website. And the class website, just in case the website is quantum.biz.unm.edu/66-22. Well, all right, no questions. I hope that means it was just blindingly clear. Next time, it is Tuesday, I'll start Fourier series, and then we'll go on to Fourier transforms, infinite series, and then complex variable theory, which may be new to some of you. Then differential equations, which of course is a subject that is so vast and varied that it's new to almost everybody in some ways. All right, well, have a nice evening. Try not to catch COVID. Bye. So I'm going to stop sharing now.